Comrade, thank you very much for that nice introduction. So I'm an interim chief data scientist. I go into teams that are lacking a senior and help the team figure out how to ship things of value. And I do that because I see so many teams not shipping things of value and struggling. And I've done like 25 years of doing all of this, including a bunch of conference talks on, hey, here's how not to screw up your data science projects. Don't make my mistakes, make new mistakes, but learn how to ship things successfully. Also, I really care about high performance computing, and this goes back like 30 odd years for me. And as Comrade noted, I'm a co-author of O'Reilly's High Performance Python. We've just signed in the contract for the 3rd edition. We'll be working on that for next year. And one of the co-founders of Pydata London, 13,000 members, nearly 10 years of volunteering now with a wonderful UK organising group behind us all. Giles will be attending in the chat, not co-presenting with me. He's my co-author of this talk, and he's worked in a bunch of big organisations like the Office for National Statistics and Shell, dealing with big data problems with tools like Dask and Spark. So what are we talking about here? Here we're going to contrast 3 data frame libraries, Pandas, Dask and Polars, one of several talks that you've probably seen here at Global this year already. There's been a lot of change in the ecosystem in the last bunch of years. We used to just have Pandas, and then to do Pandas on bigger than RAM situations, we turned to Dask. There've been a couple of other data frame libraries, and now Polars is a couple of years into the scene and is growing well. So which should you use? And here's a question for you. I'd love it if in the chat you could just go and type in what it is that you use, and Giles will keep an eye on that because we're always curious about the balance of how people are using these different tools. So do you use Pandas, Polars, Dask, or something else? When we first did this talk at Pydata London 6 months ago, we've been using Polars for 2 weeks, and we got really impressive benchmarks. I was really impressed with that. Here we've been using it on and off over 7 months and getting a bit deeper into it. One of the interesting things about our talk, as a contrast to some of the other talks, is although we use all these libraries and we know some of the core developers, we're not aligned with any one of these projects. So I don't mind having benchmarks that show that a project is doing better or doing worse. I just want benchmarks that represent a problem. What problem do we tackle? Well, early in the year with some old friends of mine, not with Giles, but with some old friends, we decided to do a silly thing. We were going to do a charity car rally, join one of these banger car rallies, where we have to buy a car more than 20 years old and less than £1,000, so a cheap old car, and drive it through Europe, 2,000 miles, up and over the Alps, over to Italy, to Venice, and back in a week, raising money for charity. Brilliant idea. It's got nothing to do with data science at all, but it gives us an excuse to get an interesting data set. Note that last bullet point. Ideally, the car shouldn't explode. You will see some peril halfway through this talk. What data set did this enable Giles and I to go and play with? Well, here in the UK, we have the Driving Vehicle Licensing Authority. They look after the safety certificates for all of the vehicles that are on the road. You can get per open data about 20 years worth of road test data for all the vehicles that are licensed to be on the road. So there's about 30 million vehicles a year. It comes as a bunch of CSV files, which all come in different formats. Every couple of years, the format changes, the joy of CSV and TSV. And you get about 600 million rows worth of data, and it's a good mix of ints and dates and strings and a few other bits. And if you go to the Check MOT service online, the government website online, you can get up, say, the records of a Volvo V50, our first car, the one that has the peril associated with it. And if you then go and look in those CSV records, you can find exactly that vehicle and its test history over the year. So we've got a nice large data set, and we use Dask to convert it to Parquet. So let's get on with the tools. Pandas, Pandas 2. So this has been out for a little while now. It was pretty recent when we gave the last version of the talk. Pandas is about 15 years old. Historically, it was NumPy based, NumPy being the numeric Python layer, allowing one-dimensional vectors, two-dimensional arrays, and n-dimensional arrays of all of the primitive types. And so this was used to provide the series and the data frames inside Pandas, which was super easy, but also came with some warts. One of the big warts being it didn't have good missing data handling. We just inherited the NAND support on floats that was available in NumPy. Then there was an extension type system added to Pandas. And more recently, in the last couple of years, we've had Arrow. So Arrow is a very different memory container, cross-platform, cross-library. So you can share data between Pandas and Polars, and between R and Julia and other systems. Anything that supports Arrow, you can share that data very easily and store it to disk in Parquet, it's the same storage system there. So that's now baked into Pandas. That's really interesting, but it's different to NumPy. And it means a lot of the internals had to be rewritten and changed to support that. And that's hurt some of the benchmarks and improved others. And also we have copy on write now. It's still off by default in Pandas 2. It'll be turned on in Pandas 3 sometime next year. That seems to be really interesting. And I've got a couple of benchmarks here. So first of all, let's have a look at two benchmarks in Pandas. So this is a 2x2 table. It looks a bit weird. So these 4 screenshots represent either string D types, so this is on the column axis, string D type, or a group by, and then on the row axis, Apache arrow, and then NumPy. So top left, if we've got a string D type, dfpda, so that's my data frame, pandas pd with arrow as a container, dfpda. I take the make column, that's the name of the vehicle, Toyota, Volkswagen, and do string length as an operation. That takes about 1 second. So that's pretty cool on a lot of rows that I've got in this data set. I think 82 million rows that are in memory. If I do the same thing on a string, and some of you who do string operations will know this, you do this on a string in dfpdn. So this is the NumPy backend equivalent of Pandas, so the default, the thing that we've been using for decades. The same operation takes about 8 seconds, so 8 times slower. That's kind of huge. And actually, if we look at the difference in memory size between the NumPy backend version of this data and the Arrow backend, the NumPy backend, 82 million rows, 39 gigabyte versus 11 gigabyte for the Arrow backend. So it's a 3-4 times memory size difference, and some operations like string operations much slower. But is it the case that always Arrow is going to be faster for us? Well, not necessarily. Sometimes the numeric benchmarks are faster, some are slower. There are some things that seem to be not yet fixed. There are some perf reports in the Pandas issue tracker, group by manipulation slow with the new engine. Some of these were fixed many months ago. However, there seemed to be a crop of them that just keep on popping up. And it took me less than a minute to find a combination on my data where I could reliably say that group by on an integer field in this case, and then taking a numeric operation, a mean, on another integer field, took 2.5 seconds with Arrow in Pandas, as opposed to just over a second with the NumPy backend. So some things are faster, some things are slower. I don't know if that's good or bad, but it's worth pointing out that if you do your own benchmarks and you're just switching over to Arrow, be aware that some things might not be as good as you're hoping for, but other things could be better. What about copy on write? So by default, and it's still the case now, by default, copy on write is disabled. This means that whenever Pandas has a data frame modification for a certain set of those modifications, and 3 of them that I've chosen here, rename, assign, and drop, they fall afoul of this. Whenever those modifications occur, then a defensive data frame copy is made. So here, if I'm making a new data frame, df2, from dfpdn, the NumPy data frame that I've been using, I rename a column. So all of a sudden, an entire data frame copy occurs. That costs about 8 gigabyte in a bunch of seconds. Then I assign a new column. That causes another data frame copy, another 8 gigabytes. And then if I drop a column, I get another data frame copy. And we could lose the temporaries until at the end, we've got 8 gigabytes, but there was another temporary during the operation. And it means that in total, 17 seconds were taken in that operation and about 8 gigabytes. And during the operation, there was another 9 gigabytes of temporary floating around in the background. So that's kind of expensive. And if we go and say, okay, row 0, test mileage column, assert the value of it, 227,000 miles. And if I modify it and then check that I've modified it and check that I haven't modified the original data frame, I get the behavior that I want. But that's kind of expensive, nearly 20 seconds for that. What if we turn copy on write on? Then we do the same operation, the same 3 things, 3 seconds, almost no memory is used at all. But later on, if I assert that my original data frame is not modified, and then I modify, sorry, I'm checking the derived data frame, then I modify the derived data frame, and then I check it and check the original, then a copy occurs for that one series that's modified, and not the rest of the data in there. So that's much, much cheaper. So that's kind of interesting. You get faster operations, and you get the correctness that you're expecting, and a much lower RAM footprint. So this will be turned on in Pandas 3 sometime next year, and you can turn it on with PD options mode, copy on write equals true. That's at the top of the screen there. That's worth experimenting with. If we have a different memory backend, do the rest of our tools work? We might assume and hope that they do, but who knows what the underlying memory requirements are. So here I did a query using Pandas and Arrow, so DFPDA, the Arrow backend, for my Pandas data frame. I took all of the vehicles that passed on this in-memory data set that I had, took a subsample of 10,000, took out the first year of use, and then filtered just for petrol and diesel engines, and then plotted on a scatter chart on the right-hand side using Seaborn, the year of first use versus mileage. You can see blue goes up on the right-hand side. That's diesel. So diesel vehicles, high mileage, but generally younger years. Those vehicles wear out and break down due to the high mileage. And in the sort of yellowy orange petrol vehicles, they can be older and they generally have much less mileage on them. So great. So we can use our Arrow backend with Seaborn and SciPy and other regular tools. What about polars? And we'll do the same benchmark in just a second in polars. So polars, it's not written in Python, it's not written in C, it's written in Rust. It's a very different backend. It was originally a data frame library in Rust, and then it became much more popular when it had a Python front end put around it, and that's the polars that we know. It's about 3.5 years old. It only understands Arrow. It has no understanding of NumPy. It can import from NumPy and export to NumPy, but internally it knows nothing about NumPy. It's only Arrow-based, one-dimensional Arrow vectors. It's inherently multi-core and parallelized, so things can go very fast in it, and that's kind of interesting. But it does have a different API. It also has beta out-of-core support for medium data. That's data that fits on a hard drive but doesn't fit into RAM, and we'll see a note on that in a bit. So let's do that same operation in polars. So looking for all the vehicles that have passed, taking a subsample of 10,000, taking their first use year, and then filtering for petrol and diesel, and then plotting in Seaborn. And here I've used a KDE plot rather than a scatter plot, but it's the same data, just to show that we can draw this using our regular tools, and it works fine. There was no problems using Seaborn or SciPy. I've tested as well. Using Arrow, so DFPLE, PL being the shorthand for polars, DFPLE, the eager data frame. So things are operated upon, every line operated upon as it's encountered with no query planning. We'll get to the query planner in a moment. Interestingly, compared to 6 months ago when we ran this exact same bit of code, polars has become 50% faster. That's really nice. To not a slow down, but a speed up, which is, and I've noticed that in polars, there's a bunch of things that just speeded up in the last 6 months. It's very interesting. Let's do a slightly more advanced query here on the left with Pandas and on the right with polars. So on the left with Pandas and Arrow, I take all the makes, all the different vehicle makes, Volkswagen, Toyota, get their cylinder capacity, that's the engine size, do an aggregate operation on them, keep all of the aggregates where there are more than 10 items so we can get a robust statistic, and then do a sort on the median value. So we could do some research into vehicles and engine sizes. And kind of weirdly, Pandas and Arrow takes nearly 30 seconds for that operation on the left-hand side, and contrast that on the right-hand side with polars and Arrow, 3 seconds, nearly 10 times faster. So that's kind of interesting. It turns out there's a regression. 6 months ago, Pandas with Arrow did that in half the time, but still 15 seconds rather than the 3 seconds in Arrow. So there's some interesting differences and changes in behavior going on in there. So some first conclusions. Pandas and Arrow may be better than Pandas and NumPy. Some things are definitely better. If you're using strings, you almost certainly should at least mix and match NumPy for the regular types that you're used to and Arrow for strings in Pandas. You just get benefits all around. And Dask is moving in that direction already. You should just do that. There's probably no good reason to stick with Python strings, the old way of handling it in NumPy. Or you could just go full on Arrow, but then some operations like that group by, maybe they're slower for you. You'd have to benchmark those yourself. Polars seems to be faster than Pandas and Arrow, and polars uses Arrow internally. And the copy on write optimization in Pandas looks like a nice optimization. It's not turned on by default, but it's recommended now that we turn it on and start testing our code, because it will be on by default next year. So you should start testing with copy on write enabled and checking that your code base works with it. Also, we've got a bunch of benchmarks here. All benchmarks are lies, so just be careful. I mentioned peril. So we bought a car, the Volvo V50. Okay, the analysis didn't drive which car we bought. eBay drove the car that we bought. But the analysis backed up the fact that we were buying this good, robust car that was probably not going to blow up on us. I owned it for less than 24 hours. About 15 miles into driving, the engine hit max revs. It turns out oil was leaking into the turbo and self-feeding itself. The road covered in white smoke. I had to do an emergency stop. By then, the cabin was filling with white smoke. I was sitting there with the key in my hand like an idiot with the engine at max revs, and I had to run away and phone the fire brigade. And all the liquid you see on the floor there, that's a mixture of the diesel and the oil and the coolant from the car. So this is one of the perils of buying an old banger car, no matter how good its provenance might be. So that didn't go on the rally because that car blew up, but we still had a good result. Right, back to data science. What if we want to resample a time series for a very common data science operation? We want to read Parquet. This is in polars now. So if I want to read a pre-prepared Parquet file, a couple of years worth of data, 2 years worth of data, I've got this one pre-prepared Parquet file. I read it into memory, into an eager data frame. And then I want to do a resample. So just like a group by or a time series operation inside Pandas. We can do all of this in polars. And you see here a group by dynamic gives me a weekly resample where I can take all of the vehicles that passed and sum them up. And that means the graph on the right-hand side, I can see that every week in 2021 and 2022, every week, typically we had 600,000 to 700,000 vehicles passing the MOT, apart from April. And in April, there's a weird behavior. Everything drops down. Now, this is into COVID. We've already had a lockdown the year before. We could hypothesize a lockdown effect is occurring here, but we can't load more data into memory because we've run out of RAM. The data becomes too large for RAM. Wouldn't it be nice if we could run the same query with almost no modification without thinking about it in polars? And it turns out we can. So if we want to scan all of the data that we've got, 850 Parquet files, 640 million rows, I change the read Parquet to a scan Parquet. That becomes a lazy operation where the query planner becomes enabled. I had a filter on just to say I want vehicles from 2018 onwards, but you've still got to touch every file to find those ones. The rest of the query is unchanged. I collect the result. It takes 13 seconds, and then I get a 5-year plot. And I can see indeed that in 2020, in April, when lockdown occurred, we get a massive decline in the number of MOTs, so vehicle tests occurring because the country's in lockdown. And in previous years, we didn't have that April effect. And in the years in the future, then the April effect is declining as people go back to testing at that point in the year and things even out again. So it's really nice that you can just swap that around and test that as you're going with polars. What if we ask an easy but larger question? What's happening with vehicle ownership per year on this open data set split by fuel types? We have to do a little bit of work here, but really we're saying for every year, so we've got to touch all of those 850 Parquet files, how many petrol, diesel, hybrid and electric cars go through a vehicle test. And vehicle tests lag new sales because you have to do a vehicle test 3 years after a vehicle has been purchased for new vehicles. So we only see a couple of electric and hybrids. But the big picture here is that the thing's going up. So more people in the UK are owning cars. Vehicle ownership is on the rise. How would we do this with Dask? And what is Dask? So Dask scales Pandas and it scales other tools. So it's often known for being the Pandas scaler, but actually it scales NumPy with the array module, and it scales regular Python containers with the bag, and it provides distributed computation regardless of data science tooling with delayed and futures. You make a task graph, you then execute that on a single machine or multiple machines, and maybe your data is distributed on multiple machines or is accessed from different sources, and then you get an output. If you're doing a Pandas-like operation with a distributed data frame, you get a Pandas data frame result back. How do we write a bit of Dask that addresses this query? Well, the naive Dask, the easy Dask solution is on the left. This is the slower one. We do a read Parquet at the top there, looking at PyArrow files. We look for all vehicles that have passed. We do a little bit of cleanup. We get the year that the vehicle was tested, and then we're grouping with fuel type, and then we can plot the number of vehicles tested per year and get that idea of the number of vehicles on the road. It takes 42 seconds. It's not bad. It's easy to read. It will execute and it will complete. There's a new tool that Patrick Hofler introduced yesterday, and you might want to catch up on Patrick's video, Dask Expressions. This is a higher level wrapper around the underlying Dask operations, which gives us a way of adding a query planner. The thing on the left, naive Dask, has no query planner. Everything is executed one item at a time, just like in Pandas. There's no attempt to optimize the query. On the right with Dask Expressions, there is a good attempt at optimizing the query. Things can be squashed together, potentially repeated computation operations can be removed from that graph, and then some of the operations can be pushed up to the Parquet layer rather than being handled in the Dask layer afterwards. By just using Dask expressions and modifying our query slightly, query wasn't implemented in the release we used, is added now. Adding optimize into our call, we go from 42 seconds down to 26, and this scales up to larger data sets. This thing's only 6 months old. Matt Rocklin, the author of Dask, told me about this after our London presentation in June, and we've been following it. So here we're testing it. It seems to work. Okay, it's 6 months old. There are some issues in there, but generally it seems to work. It's definitely worth you experimenting with it if you're using Dask. What if we better optimize our results? So we use some hard-won knowledge to optimize things. Back in June, Giles did loads of work. He spent days optimizing one of our more sophisticated queries for the earlier talk. We've kept it a bit simpler here. Here we didn't have to do that level of optimization, which is quite nice because Dask in the last 6 months has improved anyway. They've got a bunch of performance improvements in there. But by pushing some of these things by hand back to the Parquet level, even there we got a slightly better result, 23 seconds. But then contrast that with the Polars result on the right-hand side. We do a scan Parquet for a lazy operation. We have the same query in there, and it takes 24 seconds, and we didn't really have to do anything. It's kind of interesting. So we didn't have to know a lot to make a Polars work well on this single machine, multi-core, multi-file problem on one hard drive. The obvious caveat here is that Polars won't scale to multiple machines, whereas Dask can scale to multiple machines. I've highlighted the streaming equals true. On the 32 gig machine we use, this Polars query with streaming equals false, the default, it failed. It ran out of RAM. If you turn streaming equals true on, then you get kind of a batch mode running, which tries to reduce RAM pressure. And on the 32 gig machine and the 64 gig machine, the query performed just fine. So Polars should work even if you've got very large data sets with very large queries with this experimental streaming mode, which is kind of interesting. So we haven't checked lots of things. There's just a lot to test, right? And with changes, fundamental changes like copy on write coming through in Pandas and Arrow coming through, where some benchmarks improve and some get worse, and some sub-libraries no longer work the way that they used to. It's kind of hard to figure out all those permutations. One thing that I do use in Pandas is number. You can use an engine equals number some of the time to make some of your operations compiled. And in one of my courses, I teach how to use number to make your numpy-based code run compiled. Number doesn't understand arrow, so number can't be used on arrow-based columns inside Pandas. So we lose a bunch of our optimizations that occur. So if you're doing lots of numeric heavy work with an engine of number, you might want to stick with the NumPy data types. And I'm not sure how that's going to evolve because I don't think number can understand arrow, at least at the moment. There's some different handling of NAND versus missing data between Polars and Pandas. It's worth reading up if you're going to Polars. You definitely want to read up on how missing data is handled because Arrow behind the scenes has a different way of representing it. There's only partial Scikit-learn support because Scikit-learn assumes the Pandas API and Polars does not have the Pandas API. Scikit-learn could replicate the Polars API or the Pandas API, but then there are other APIs and I don't want to replicate all of them. So there's work for a data frame interchange protocol, but that's in quite an early stage at the moment, so that's not yet supported. And then other things like arrow time series and strings, maybe they have different behavior. They do have some different functionality between NumPy and Arrow. So it's not an easy clean swap. Maybe on large code bases you want to go very slow. It's definitely worth experimenting with Arrow, be it in Pandas or Polars, for greenfield projects. I found Polars easy to use, both when I first learned it and then subsequently. Pandas, of course, we all know it. Arrow's great in both. It does seem to at least reduce the memory pressure for a lot of operations. There are some differences. Polars, for example, day of week starts counting at 1, whereas in Pandas it starts counting at 0. And some operations in the lazy API in Polars are missing, like sample. And Dask also, because of its lazy computation nature, also has some things that are missing from Pandas. So just be aware that there are some more edge cases you have to think about as you try to move over. I will note that when I started learning Polars, it frustrated me because it told me I couldn't do things, but it guided me in the right direction. And it turns out it makes my thinking easier as opposed to Pandas, where there are 20 ways to solve the one problem that you're trying to solve. So Polars kind of forces you down the right avenue towards an efficient computation that is clean. And that's kind of nice. So I quite like it. I think for medium data that's bigger than RAM, Dask and Polars can perform similarly. Dask has a harder learning curve, particularly if you want to go down the optimization route, but it also has support not just for Pandas data frames, but NumPy and standard Python functions with delayed computation and machine learning, distributed machine learning, and it has really, really rich graphical diagnostics. If you're doing single large machine or multi-machine computation, the diagnostics and the ability to cloud host that in Dask is really kind of interesting. So it leads to a very, very scalable solution if that's the kind of data set size that you're working on. So back to the rally. We won it in the end. It turns out it wasn't a timed rally. You had to do challenges every day. We did that. It was a charity rally. We won it. We got a bunch more money. So we were able to give a donation of several £1,000s to Parkinson's in a Volkswagen Passat estate that was 24 years old and which did not blow up on us. It didn't have a turbo, so mechanically it was more sound. Next year, maybe I get some vehicle telematics with a Bluetooth dongle. Maybe I can do a richer talk on engine dynamics as we do the rally again next year. Summary. Hey, look, it's time to experiment. If you've got greenfield projects going on, we've got interesting options. You should definitely try Dask. You should definitely try Dask expressions, where you get the optimizations on top of Dask. You should try Polars, and you should try copy on write in Pandas, and you should try the new Arrow backend. You should just experiment with these things. I'll be covering these in my high performance book for the 3rd edition, which will be out in a year or so. You may just see up on the wall behind me, there are things on the wall that you can't really see. They're postcards that people have sent me. If this talk or other talks I've given in the past have educated you, I'd love to receive a postcard. They make me happy. Send me a postcard when you're up a mountain. Just send me an email. I'll send you my address. I'd love to receive postcards. And I talk about some of these things on my email, on my newsletter, notanumber.email. I'll put that into the chat afterwards. And I'll be talking about all the new things that I discover in Polars and Pandas as I carry on with this journey. And right now, I think we've got a couple of minutes for some questions, maybe, and maybe Giles has been handling those. Thank you very much for listening. Right, I'm going to stop the slide share. Oh, I see the hearts coming up the screen. That's brilliant. Thank you very much. Oh, I see Giles has been dealing with all the chat. That's brilliant. Excellent. Comrade, is there anything that's that we need to answer?
There is a question in Q&A. Is there a project or effort for multi-machine polars?
I believe yes is the short answer. I believe that's the case. I know when Richie started the project, he said absolutely it would not do, it was only in memory, it wouldn't do streaming data and it wouldn't do multi-machine data. And then he changed his stance on streaming, and then I've seen a change in stance on the multi-machine. I don't know when or how that happens, but I believe there are at least investigations. And if you search for Coiled, so Coiled is the commercial company that backs Dask, the open source project. Matt Rocklin, there, the author of Dask, has done some okay, you're very welcome. General design considerations for Dask versus Spark. Oh, I don't know if I don't know. I don't have a clean answer to that one. It looks like Pandas to improve performance and memory footprint. Are there still room for improvement? Of course there is. Pandas is slow. Pandas is single core most of the time. Pandas does not have a query planner. There's loads of things that could be fixed in Pandas, but Pandas was never designed to operate that way. So it's really hard. There will be more performance improvements in Pandas. The team behind it worked really, really hard to support us in the wider community. You should always thank the Pandas devs because they've got a really tough challenge. It's a really popular library that supports lots of different ways of executing lots of different queries. They do have big plans. Polars is interesting because it's a new project, so it's got to watch Pandas over a decade and PySpark and other distributed data frame tools, and it's had a chance to build an API around all of those learnings, whereas Pandas kind of has to play catch up there. So yeah, interesting differences in those projects, but there is definitely room to grow in Pandas for things to get faster. Right. What else do I see in there?
View on DuckDB, and this is probably the last question.
Oh, do I have a view on DuckDB? I don't have a view on DuckDB, except that if you want to read CSV files, you can just point DuckDB at them and query them with SQL, even though they're very large, and it just works, which is dead impressive. No importing, it just worked. And I've had other people tell me that in some communities, DuckDB is Pandas. No one uses Pandas there. They use DuckDB, and it has for their problems similar performance for large, certainly Parquet columnar data sets. So I think for the right use case, DuckDB is a very, very solid choice. And Giles has linked to a benchmark in there: Spark, Dask, DuckDB, and Polars, the TPCH benchmarks at scale, which Matt Rocklin did recently, and that included some comments about Richie Vink and the collaboration. That's a really good video to watch, and that shows some of the performance differences for medium and large data sets with DuckDB versus the other tools. It's a solid tool. I know people who use it and love it, so DuckDB is worth a consideration.
Cool. Thank you, Ian. Thank you, Giles. Always a pleasure.
Thank you very much.
And I think that concludes our talk. And our keynote session is coming up next. So see everyone else there.
Great. Thank you, comrade.
See you guys.